Is up next. He is from the Karlsruhe Institute of Technology, aka KIT. His presentation is entitled "Storage as a Computer," and he should know because he's deployed a whole lot of it. So without further ado, does your microphone work?
It worked before. The static there. Okay, thank you. All right. Well, thank you also DDN for inviting me here to give a short rundown of what we do at KIT, especially in the Computer Center of KIT SCC, with storage, and I'd like to expand that a little bit towards data management, because I feel that storage, although there's a lot of things that we need to solve still, is something that we at KIT like to close and leave behind us, because we can stand there on the research that DDN does for us and others do for us. We are more or less moving towards the application level, data management level. That's why I put it that storage is the computer. I don't think Scott would mind dubbing this, because I'm looking at storage more today not as putting it on a disk, but as managing a lot of petabytes in concert. As I said, I'm speaking here on behalf of the Computer Center of the Karlsruhe Institute of Technology. We have a joint, we are a joint company that was founded, it's an institute founded a few years ago when we joined together with the university and the research center. That's why we have two buildings, so there's a big pipe in between that sends data over. And there's a lot of, in the portfolio we do high performance computing, scientific computing, all these things that you find regularly and in computer center of the university. But above all, we do grid computing and since a short time also cloud computing. But we're specializing in large facilities. And this is where especially DDN comes in, and I'd like to continue there, with two of those large facilities that we are operating at SCC today. First of all, there's of course the GridCA facility, which is an LHC Tier 1 center. As you may know, the LHC computing is a distributed thing, which is distributed over something like 10, 11 centers. And in Karlsruhe, there is one, this is the German Tier 1 center. There we are supporting, in fact, all 4 of the LHC experiments, and there is currently about a 10 petabyte. I lost count a long time ago, something like 10 petabyte storage. I'm not sure I think it's even usable for storage, but I think Tuan would even know better than I how much storage we actually have today at GridCA. We do there mostly operations for LHC computing. We install software, we run the software that we get from these experiments. We also use storage data management systems that are developed elsewhere. And in our case, this is Dcache and XRD. I will talk about those things a little bit longer later, because I think that some of you in the audience may be interested in those solutions for data management. Since a few years we've engaged in a new undertaking, which is support for data storage, data management, and in fact a set of services for other sciences than particle physics, because LHC computing is of course typically physics computing, where we do in fact the work that others more or less advise us to do. And in the case of the LSDF, the Large Scale Data Facility, we actually are working on supporting an infrastructure, building up an infrastructure for sciences that are also in the need of data management, of IT infrastructure, but we're not as organized as a physicist are. I made also some pictures of our, because it always shows nice photos of our DDN environment. There's a lot of storage. The 10 petabytes still fills I think something like 14 or 15 racks. It's more or less compact today. This wouldn't be possible, of course, let's say 5 or 6 years ago. In fact, our computer center is now shrinking at the moment, although LXC computing is still adding storage, and also the LSDF project adding storage. But we do not need all the floor space anymore that we had provisioned. We put 10 enclosures in a rack, and then there is still room left. Let's see if I can get this to work. All right. There is still some space left for a controller or singlet. Since two racks, we put 2 racks next to each other, and there's a singlet in one rack and a singlet in the other rack, and then the wires go, I think, underneath or above and are connected. So we have, this is the grid card environment. We have 20 enclosures behind the couplet of SA 9900, I think. It's one. That's one, 9900, right there. And there's more storage. These are all different racks, but not there is also some OEM storage. So this is IBM. We bought this a few years ago for a special project. And interesting fact was that we had some maintenance problems, and then IBM said to us, well, we don't even know this system. Please tell us what it's about. They couldn't reference it, and luckily enough, our local in fact, one arranged for support for that. So we got it supported and maintained, and now everything is fine there. It was a little bit interesting to have this experience where IBM would say, well, we have no one in Europe that can actually support us. This was a few years ago, and I'm pretty sure it's better nowadays. As I said, we use racks that are pretty high, 42 height units. They're completely closed with, so there's a confined space where the air is circulated through a condenser, and then cooled. And 10 disk enclosures are in one rack. And there is, I think, 2 height units are used for the environmental control. We could put a complete DDN storage system with 10 enclosures and a couplet into a rack, but we need some space for the rack environment control. Summing up all these parts of DDN, grid car, LSDF, and then the counter systems. I have to change this here again. It's better? All right. There's a lot of 9900s, a lot of disks, but I'm pretty sure people here in the room can top that. All in all, I came to about something like 13,700 terabytes, maybe plus or minus 100 terabyte is raw disk capacity. This also shows a little bit of the issues that we're encountering, because this awful lot of number of disks, not only is it a floor space, but it takes a lot of walking, opening doors, opening enclosures to get this maintained. Luckily, of course, people from DDN are assisting us there, but still having these installations is a major undertaking, and it's not always that easy to have thousands and thousands of disks managed. This is just a storage system again. I said in the beginning, I'm not actually interested in that any longer, but it still has to be done, of course. It's one of those basic facts in the computation center. A short environmental thing, what we have it all these facilities is that we do the networking with Cisco, we have a Sun with Brocade. Everything is running Linux. It's a flavor of Red Hat Scientific Linux. Nothing is adapted there, no special features, no special adaptations. Although we have some drivers that we take directly from the vendors. It's all GPFS, so all the storage is running on the GPFS. There are small exceptions, for instance, in the HPC, in our HPC environment, in the other computation center that we have. There is a cluster system running on top of the DDN system. That's really the exception. And the data storage is done, as I said, with Dcache and XRD. I'll come to that later. There is a HTML backend, which is based on TSM. Pretty much standard tools and standard environment for those of you familiar with that. A little explanation how this, on a high level view, we combine all this storage. Is not just a big file system. We're not pushing these 10 gigabyte per second speeds that John was talking about. They were doing, but we have these building blocks where you have something like 2 or 5 nodes wrapped together in a small cluster. This gives us some redundancy because we can move the application from one node to the other, either for maintenance of the node or even if a node fails, we'll just start it up on another node. This can be done by people that are on call so that we can guarantee our service levels. All these disks, we have, as you can see, there's a lot of disks connected to a single controller. So the environment is mostly capacity. So there's something like a petabyte behind the controller on raw disk capacity, and this is moved to a few nodes. So there's no actual, let's say, we don't need the speed at the moment in this environment, which is mainly the physics environment. This will change, of course, for these other sciences that we're working on serving. Anyway, another high-level view where we have this, as you see in the bottom, the GPFS file system. On top of that, we have Dcache or XRD or NFS, because NFS is also exported there. Most of the actual data management is then done by the users of our systems in the physics computer. They have their specific data management that they bring along. So moving data from one side to the other, or even within the site, is being done by software that has been developed on behalf of the so-called VOs, the virtual organizations. This is all grid-like. Now, one of the key components in this structure is Dcache, and since a few years also XRD. I'm not going into detail there, but what is most important is that this software allows you to group single entities, single storage islands into a single namespace. Both systems do that. Dcache does this in a way that the actual metadata management is like the cluster is put on a database, and all traffic, all the data traffic is directed to individual nodes. And XRD does not have this database, but is similarly working in where a client connects to the system and then is forwarded by the system to the node where that data is actually located. And both systems are in fact managing today several petabytes. I think that Dcache is installed in 7 or 8 tier 1 sites. And it's therefore a big, well, it all runs on top of GBFS, of course, but actual data management would be unthinkable without this software. Same for X-Routine. This is still something that is not as widespread as Dcache in LHC computing dolls, LCG environments is coming. However, the difference is that there is no database involved, so everything is still taking place at the level of the storage system at the file system level. Again, below all these systems, these both systems, there's GBFS. So everything, in fact, so all the I/O is done through GBFS, and so all the overhead clauses are still going down to GBFS. And sometimes this is actually limiting both systems. Both systems, by the way, they scale to many petabytes, and they can be really many petabytes. So you have one file system addressable. It's I used to call it the file system user space. You can actually see several petabytes behind one system. And it has a lot of bells and whistles, of course. One of the things that X-Routine doesn't have is so-called SRM, which is a resource management interface that was developed as a kind of intelligent interface to manage large data sets. It didn't come that way, but in X-Routine it's not there. So that's the reason that it's not that widespread in LHC computing. Okay, as I said, we're also looking at other sciences to serve and to help them, in fact, more with data management issues, with data storage issues, because most of these sciences, they have started to put everything on a USB stick or on a CD, and they put it in a cupboard, and then later discover they have to reread the data, and they're not able to do that. They cannot find the data. But still, these people, they are producing a lot of data. Biology, I'm only talking about institutes that are on campus in KIT. They are producing hundreds of terabytes per year. Those are images. And they're putting, what they used to do, they put these on portable disks. So they buy these portable disks, and they have these racks full of disks that are taken from the casing, and they put a label on it and say this is a measurement 1 to 10 or something like this. And if you want to rerun a computation on a certain measurement, you have to go outside and take the disk, carry it to a kind of station where you put in the IDI connector. So they have these little facilities, and they put the disk there, and then they start reading it. Of course, you have to mount all these things. It's not very ideal. The same thing with synchrotron radiation. People, they do material research. They produce a lot of data with imaging equipment. Climate research, this is a very special case in our case because they need to keep the data for a very long time. And this also has its own quality, because keeping data for a long time means longer than 1, 2, or 3 disk generations, or data storage generations. Even if you're capable to do that, storing it for a long time by maybe copying it, it's also necessary to know that the data is still intact, that the data is still the same data as you put it on the disk. These are special things. I'm not sure if DDN can help there, knowing that the data is still the same data when they stored it, but this data integrity is especially important in the case of archiving. Now, these sciences, they see that they know that of course the data in these sciences, as I showed, is growing, but they have very special questions, and that's why I come to this point where the storage system computer it's not just about storage, it's about managing data there. And they have very specific questions to us, and they come to us, and I'm sure there are other people here in the room that are asked the same questions. So they need to have accessible data, they need to get the data from everywhere. These people are mobile, these people are working in large communities, and they need to be able to access data from all over the world. Of course, it has to be fast, because they still use a kind of HPC environment. And the finding, as I said before, is a very special topic. At the moment, they can get away by storing data on USB sticks or portable disks or whatever. They already recognize this is no longer possible in the long run. So we started to design a special environment called Large-Scale Data Facility to support these sciences. And this is a combination of HPC and large-scale data storage and a special environment. It's still in its infancy. However, one of the things that can be seen already, of course, we have some data direct storage in there. There is also some IBM storage, pure IBM storage, not OEM storage. Basic building block, of course, a 10G network, which is level 2, I think, all over the place. So that means that even people at the institutes can access the data at a high data rate. And the greatest difference between, the largest difference between the other large project with this LSDF project is that we have computing directly attached to the storage. Now, for many people in HPC, this may be a common fact. It was not this way in the LHC computing, where you always had this difference in storage nodes and accesses through data management systems. Here it is that the storage is in fact integrated with the computing. It's so-called data-intensive computing environment, although access still is still possible through NFS and SIPs and such. On top of that, we have started to work with IROTs in cooperation with DDN. We are looking at a system they have in their portfolio called WAS. We're hoping to set this up during summer and start some transfers over the ocean, and also use IROTs as a data management system. And I'd like to pose the question here. We still are looking for people that are willing to join us in this experiment across the Atlantic Ocean, or on the other side of the Asia Pacific, or something. Since a few months, we have joined forces, and I'm coming back at this data management thing. We have joined forces with several institutes of the Helmholtz community. We have come up with a proposal that we're 2 minutes. We've come up with a proposal where we'd like to, where we say, well, we can, if we join our forces, we can build a good system. That's a very good system to support all these other sciences that are nowadays struggling with their petabytes, or they don't know that they're struggling with their petabytes yet. But we can tell from our experience, because all these people have experience with large data systems. And we have identified 4 teams that we are sharing there to support these sciences. A lot of those things, of course, are pretty familiar, but it turns out that although you see a lot of solutions here also at the exhibition hall, there's no integrated solution. If someone from biology is generating a few terabytes of data per day, he cannot go to a vendor and ask, I'd like to have a data management system for my application, for my environment. He has to shop around, which is easy for us to say because we know IT. But these people very much are unfamiliar with that. In fact, they're not even interested in it. They want to do their science. And they're not computer scientists. These are biologists, these are librarians, these people are people from all kinds of, as I showed, climate research people and such. So there's a lot that we threw in a basket where we put all these components together and started up sketching a blueprint which will slowly fill in all the blanks to help these sciences do their own data management the same way or even more effective than current LHC computing, because they will use our experience with LHC computing. I'm going to a conclusion now. To my opinion, to our opinion, storage, of course, is important that we should move to the services above that. I mean, I'm not saying again that storage is a sole closed book. However, for someone that likes to store data, they always say, well, we'd like to manage data. We don't want to store data. Of course, they'd like to store data first, but if you have a petabyte, you have to manage data. This is where we come in with this other focus. And I also think that that large facilities like ours should be able to do more than just storage or computing. If you offer a batch system, that's not enough. If you offer a Lustre, that's not enough. If you offer GPFS, that's not enough. You need to add a package there so that people can actually use your storage. So that's kind of a message here. In the future, there will be a data management and analysis infrastructure, ART, that will be shared with other Helmholtz institutes. So it will be a German thing, and since we're also participating in UDOT, this will expand beyond the borders of Germany. We're engaged already in this WAS-IROS test. We're setting it up. This will be during this summer. Of course, it will be expanded. In fact, we're looking at an expansion next year, because then our current contracts run out, our maintenance contracts, and we have to do another replacement of the current storage and expansion of adding more storage for the next requirements. IPv6 next more, IPv6 networking is of course a topic that we really like to address, because if you're building up a new infrastructure, it might as well be IPv6, especially because our network people said, well, we don't have these IP addresses that you're requiring, even in our case. Cloud storage is of course there to enable a low effort access all over the world to storage. And of course, we are preparing for the exabyte storage. I think that in our case it will be around 2020, and I think that the next speaker will talk about exascale storage. So I'm leaving it here. Thank you for your attention, and hope to see you in private later.